Good evening, friends. I hope you're all fine. Today's lecture is about the mean value theorem. We are in section 2 of chapter 4. Previously, we have talked about, last lecture, we talked about global maximum and global minimum in the first section of chapter 4. That means we talked about the extreme values. Okay, what were the extreme values? We said when we say, let me make a quick review as we do in general. We have got global extrema. Okay, global extrema. We said, what does this extrema mean? That means global maximum and global minimum. Okay, how were we finding this global maximum and global minimum? We had a procedure that we were finding the critical numbers of the function that we had. Then we were inputting the critical numbers with the endpoints of the interval into the original functions. We were taking the greatest value and the smallest value. We could get maximum and minimum values or global extrema for the function that we had. Then we came to what? After global extrema, we came to relative extrema, or okay, global, we said, what can we also call it? As absolute extrema. We have got relative or local extrema also. What are these ones? These ones are also maximum or minimum points for a function, but of course this one is again max and min. But when we are talking about the global extrema, we said we are talking about the whole interval of the function that is given to us. Okay, for example, if you have got a function like this one, okay, from A to B, okay, we are talking about maximum, global maximum and minimum on that interval. But when we are talking about local extrema, what do we have? We have got sub-intervals. That means we are dividing the interval that we have got. For example, if you have got something like this, we are dividing the interval that we have got into sub-intervals, and then we work on it. We see on which interval. For example, we said on that interval if it has got maximum or minimum, on that interval if it has got maximum or min, these ones will be called local extrema, and on the whole interval without subdividing it is called global extrema. Okay, today's lecture, as we said, it is about mean value theorem. But before talking about mean value theorem, what do we have? We have got Rolle's theorem. Rolle's theorem then is used to prove the mean value theorem, although the proof is not required from you of mean value theorem. But studying Rolle's theorem will make the mean value theorem to be understandable in an easier way. Okay, so what do we have in Rolle's theorem? It says we have got a function f of x which is continuous. Okay, so what do we have? We have got a function f of x that is continuous on a closed interval a and b. So what do we have? I'm drawing the function for the case that we need. I have got a function, for example, consider the function that we have got is like that, and the interval that I have got, say I have got here interval a and b. So that is the function that I have got. If you look at the function on that given interval, it is continuous, and it is also differentiable at every interior point. So I also have got another condition on the function that it should be differentiable, that means I can take the derivative of that function on the interior of that function. That means from a to b, but without endpoints. Okay, it says if f of a is equal to f of b. What does that mean? F of a is equal to f of b. If you look at that function there, if I put a into the function, I will get that point. Okay, and if I put b into the function that I have got, I will again get that point. If you look at this one, if I draw this, what do I get? I get that f of a, that's of course f of a, okay, and that point is f of b. If I see their y's are the same, okay, it says if f of a is equal to f of b, okay, I'm putting this one into the function and that one into the function, I get that these two are equal to each other. then I can definitely find at least what number C in AB, that means in that interval, I can find a number where if I put that number C, okay, into the first derivative of the function, and I will get 0. What does that mean? That means if I have got a function like that, okay, continuous and differentiable on that given interval, if I draw a horizontal line and it intersects, okay, a horizontal line, and it intersects the graph of the function at two different points, what does that mean? That means those two numbers are equal to each other. Then I can find a tangent line to the curve. Okay, here, if you look at this one, I have got a tangent line to the curve where its derivative is equal to 0. Okay, when I'm talking about the horizontal line that is intersecting two different points and makes them equal to each other, what does that mean? In other words, that means the function has got a tangent line, okay, parallel to the horizontal line, of course, has got a tangent line where its derivative is equal to 0. Okay, so we have got a number C here. Okay, that's between A and B. I found a number C between A and B, where when I find the derivative of the function and I input that C, okay, that number into the derivative of the function, I will get 0. Of course, the conditions are important. Being continuous, being differentiable, these ones are important. Why? For example, if I have got a function like this, okay, I have got something like that. If you look at this function that I have got, it is not continuous. If you look at that function here, let me put this one here. Okay. If you look at this function here on the interval a and b, if you look, f of a is equal to f of b. I have got a horizontal line that's passing through both of them and makes them, sorry, this one is f of a, and makes them equal to each other. But since the function is not continuous, what do I have? The first condition, it says f of x must be continuous on every point on the closed interval. But since if you look at the function, I have got the function is not continuous. Since it is not continuous, so I cannot find any tangent line that makes the derivative equal to 0. So I have got discontinuity here, okay? It is not continuous. So that one doesn't hold, doesn't make the Rolle's theorem hold, okay? Or if I have got, for example, something like that, okay? If you look at that function, here again I have got a, and that is b. Again, f of a is equal to f of b. If you look at that function, is it continuous? Yes, the function is continuous. I have got no problem in continuity. But since the function is not differentiable at that point, because I have got two things here, it says the function must be continuous on AB and differentiable on its interior points. Then if f of A is equal to f of B, the continuity and differentiability must hold, then I can talk about being those two values must equal to each other. I can find the C. But here, if you look at that function, it is not differentiable at that point. So the differentiability does not hold. That's why I cannot find a tangent line here where the where when I put that C, number C in it, it makes it equal to 0. Okay, so what are the conditions? First, I have to verify that the function that I have got is continuous and differentiable on the given interval. Then I can talk about Rolle's theorem if f of a is equal to f of b. If you look at here, f of a is equal to f of b, f of a is equal to f of b, but I cannot then find the number c. Why? Because the first two conditions of continuity and differentiability doesn't hold. Okay, so let's move to the first example that is given to us. It says verify that the Rolle's theorem for the function f of x that's equal to x squared plus 1 on -2 to 2. What is given to us? a function is given to us that's equal to x squared plus 1, okay, on a interval. If you look at the interval is from -2 to 2. If you look at that function in general, you know that x squared, the function x squared is what? It is a differentiable, I mean it's a continuous function, the first rule of Rolle's theorem, and then it's also a differentiable function. I can find the derivative of that function on the given interval. Since continuity holds, okay, and differentiability holds, then I will check what? Okay, continuity holds, differentiability holds, then I will check if f of a is equal to f of b, okay? I'll put the endpoints into the function that I have got. F of -2, I'll have to find also f of 2 to see whether it holds the Rolle's theorem conditions or not. Okay, f of -2, if I put -2 into here, what will I get? I will get that's equal to 4 plus 1, and that's equal to, of course, 5. That one is 2 squared plus 1, that's also equal to 5. Since f of -2 is equal to f of 2, so by Rolle's theorem, okay, so by Rolle's theorem, there exists a number c that's equal to 0, the number that is between -2 and 2 is 0, such that f of 0, I mean f prime of 0 is equal to 0. The procedure of finding that c is not given to us, okay? How do we find that c? It's not given to us, so not every time it's required from you to find that c, okay? But if it is easy like that example, you can simply find it. How can we find it? We are finding the derivative of the function, okay? Because I'm working on the derivative. What is the first derivative of the function? It is equal to 2x. I'm searching for that x that makes this one equal to 0. So f prime of x is equal to 0. What does that mean? That means 2x is equal to 0. What does that mean? That means x is equal to 0. So the number c that I'm searching for is equal to 0. Okay, sometimes it is easy to find that number c for Rolle's theorem, and sometimes it is not. Now we verified Rolle's theorem for that example. What did we have? We were given a function that was continuous and differentiable on the given interval, and we saw that when we put the endpoints into the function that we have got, they are equal to each other. So by Rolle's theorem, we can find a number c that if we put it in the first derivative of the function, it makes it equal to 0. Now we are coming to mean value theorem. We said, why do we study Rolle's theorem? To find, to check on the mean value theorem. Okay, we have got the mean value theorem. What does mean value theorem say? It says, suppose that f of x is continuous on AB and differentiable on the open interval AB. In general, we call mean value theorem as a slant form of Rolle's theorem. Why? Because Rolle's theorem, when we were talking about the function that we had, we were drawing a horizontal line, okay, making f of a and f of b equal to each other. But when we are talking about mean value theorem, we are drawing a slant line that makes those two numbers, of course, not equal to each other, that we will work on, okay? So what do we have? Again, we have got f of x must be continuous on the closed interval and must be differentiable on that open interval. Then we can talk about mean value theorem. If continuity and differentiability hold on that interval, then it says what? We can find at least one point c in that interval such that f prime of c, that means if I find the derivative of the function and put that number c into the derivative, I will get that is equal to f of b minus f of a over b minus a. How is the graph drawn here? I mean the graph of the function. We can say, if you look at this one, let me draw a function. I have got, for example, a function like that. If you look at this one, Rolle's theorem will not hold for this. Why? Because in Rolle's theorem, we are drawing a horizontal line. Okay, no horizontal line can intersect 2 points of that function. So Here I have to draw a what? A horizontal, a slant line. I will draw a slant line like that, from here to there. Instead of a horizontal line in Rolle's theorem, here I have got a slant line. Here is the point A, the closed interval that I have got, and that is the point B. Okay, that is the interval that I have got, A and B. If you look at this one, I have got f of A here. Okay, but here I'm not saying f of A is equal to f of B. This one is only true in Rolle's theorem because we are drawing a horizontal line in Rolle's theorem, but here we have got a slant line. I cannot say that f of A is equal to f of B, although it is intersecting 2 points. Okay, these ones are different, but I'm working on this one. Okay, so what is the slope of that slant line? Here I have got the point A and f of A. Okay, and here this point is B and f of B. How can I find the slope of this one? In Rolle's theorem, we were saying that f prime of C is equal to 0. Why? Because a horizontal line, okay, a horizontal line's slope is equal to 0. But here I have got a slant line, so I have to find the slope of this one. What is the slope of that line? That's equal to f of B minus f of A over b minus a. If you remember, we have got y1 minus y2 over x1 minus x2, but here instead of y1 and y2 we have got f of a and f of b. Instead of x1 and x2 we have got a and b. So that is the slope of that slant line. So since we have got a slant line and we have got the slope is equal to this one, I can find a tangent line here, okay, such that if I find the derivative of this line, since this one is parallel to this one, so their slopes are equal to each other. If you remember from chapter 1, I think we have studied, if you have got two parallel lines, their slopes are equal to each other. So f prime of that C that is between A and B, okay, that C is equal to that one. So f prime of C is equal to the slope of that slant line. That is the mean value theorem. So it is in general called the slant form of Rolle's theorem. Now we have got a procedure. Of course, finding that C here is very easy, like we did previously for the Rolle's theorem. We're given an example. It says find C in the mean value theorem, or using mean value theorem in the mean value theorem. What's the first one? I'm given a function f of x that's equal to x squared plus 2x minus 1. Okay, and the interval that's given to me is over 0 and 1. Using Rolle's theorem, I mean mean value theorem, what do we have to check? We have to check on continuity and differentiability. That's a polynomial. It is definitely continuous on that interval, and it is also differentiable on that given interval. It's required from us to find that C. So how do we find that C? I will say f prime of x is equal to what? F prime of x, finding the derivative of this one because I need the derivative for putting C into it. That's equal to 2x plus 2. F prime of C is equal to what? Is equal to 2c plus 2. And then I have to find that B. So f prime of C is equal to what? F of B minus f of A, that is A and B, all over B minus A. So that one is equal to what? F of B minus f of A. If I put 1 into that function, what will I get? F of 1. If I put 1 into here, I will get, let me write it here for you. That will become 1 squared plus 2 multiplied to 1 minus 1. This 1 and 1 cancel each other, so I will get 2 minus f of a. If I put a into here, that will be 0 squared plus 2 multiplied to 0, so that will be negative 1, all over what? B minus a, 1 minus 0, so that one is equal to what? 2 plus this one, that's equal to 3 over 1. What have I found so far? I have found this one, and f prime of C is equal to this, so 2c plus 2 is equal to 3. Okay, because f prime of c is equal to this one, and I found this one that's equal to 3, I put it here. Let's solve that equation for finding c. I will get 2c is equal to, taking this one to the other side, 3 minus 2, that's equal to 1. So c is equal to what? 1 over 2. 1 over 2 is between 0 and 1. So since it is the function that I have got is continuous and differentiable on the open interval of this one, of 0 and 1, so I could find that c that's equal to 1 over 2, which is between 0 and 1, so that if I find the first derivative of the function and if I put that 0 into here, I will get 3. I mean, if I put that 1 over 2 into the function, the first derivative of the function, I will get 3. That's mean value theorem. Let's do the second example. The second example, we have got the function f of x that's equal to x to the power of 2 over 3 in the open interval, I mean on the closed interval 0 and 1. First, let's rearrange that function. Okay, of course, for finding the derivative, it's easier like that, but for inputting the value, it is better to change this one back to its normal face. This one is x. We said the 2 is here and the cubic is there. What is the first derivative of that function? Because we need it for f prime. If I want to find the derivative of that function, that's equal to 2 over 3 x to the power of 2 over 3 minus 1. You know, the power decreases by 1. So that's equal to 2 over 3 x to the power of, I have to equalize the denominator of this one with that one. So it will be 3 over 3. 2 minus 3, that's equal to minus 1 over 3. Okay. How can I rewrite this one? That will be 2 over 3, 1 over x under the cubic root, because the negative brings it down, and 1 over 3 gives the cubic root. Okay. Now, how can we calculate this one? Of course, I have to find f prime of c because I'm searching for that c. That will be 2 over 3, 1 over c under the cubic root. Now, I know that f prime of c, that means 2 over 3, 1 over cubic root of c is equal to what? F of b, that means if I put b into here, what will I get? 1 squared under the cubic root, that's equal to 1, minus, if I put f of 0, because the rule that we have got is just f of b minus f of a, that means I'm putting a into the function. If I put this one 0 into here, what will I get? 0 over 1 minus 0, b minus a. So from that one, what do I get? 2 over 3, 1 over cubic root of c, that's equal to 1 over 1. Now, simply we can solve this one. Okay, that will be 2 over 3 is equal to cubic root of c. I simply multiplied both sides with this one, or you can say we did cross multiplication. So taking power for both of the sides, okay, the third power, this 3 will go with that 3, and this one will give me 2 to the power of 3 is equal to 8, and 3 to the power of 3 is equal to 9, so c is equal to 8 over 9. So if I put that 8 over 9 into the first derivative of the function, what will it give me? It will give me the value that's equal to 1, because that's f of b minus f of a over b minus a, or we can say that is the slope of the slant line that we have got. Okay, we have got other examples, but the examples are also all easy. You can do it yourself. That will be a small exercise for you, because already the solutions are given in the course material, but I think that is enough for you to understand how to use Rolle's theorem and the mean value theorem. So I will leave the other examples for you. Sorry, here we have got 3 to the power of 3 is equal to 27, not 9. Okay, 27. Okay, we've got the last example. It says checking and using hypothesis. Okay, let me write it for you. Checking and using hypothesis. Okay, what is using hypothesis? The hypothesis of Rolle's theorem and mean value theorem is that the function that we have got must be continuous and differentiable on the given interval that we have got. So let's check the first example that is given to us. Let's check if we can use Rolle's theorem or mean value theorem for this one. We have got f of x that's equal to x to the power of 2 over 3 on the interval -1 and 8. Is this one differentiable, continuous or differentiable on the given interval? Let us first rearrange this one. That's equal to x squared under the cubic root. So on the interval -1 to 8, the function that we have got is continuous. So continuity holds. Okay, because whatever number I'm inputting into here, it is fine, it gives me continuity. Let's check the derivative of the function. If I find the derivative of this one, as we found previously in here, that's equal to what? That's equal to 2 over 3, 1 over cubic root of x. If you look at that function, that's the differentiation or the derivative of that function. If you look at that one, is it differentiable on that interval? If I put -1, it doesn't make a problem for me. If I put -12, doesn't make a problem for me. But here in between that interval, I have got 0. If I put 0 into that function, will it make it something defined? No. Since I have got a number in that interval that makes the first derivative of the function undefined, so the function is not differentiable on the interval -1 and 8. So the mean value theorem hypothesis does not hold for that function. Okay, what did we do? If you check, it is just asking if the hypothesis of mean value theorem hold or not. What are the hypotheses? We have got continuity and differentiability on the interval that's given to us. We checked the function, it is continuous on the function, on the interval. Okay, it doesn't make a problem for me on each of these points on the interval from -1 to 8. But when I took the derivative of the function, I have got 0 that makes the a problem for the function. So I cannot say that it is holding the hypothesis of mean value theorem. We have got another example. F of x that's equal to x to the power of 4 over 5 over the interval 0 and 1. If you check that function, that one is x to the power of 4 under the 5th root. Okay, is that function continuous? Yes. Why? Because whatever number I'm inputting in on that interval, it makes it defined. Let us find the first derivative of the function. So what do I have? Continuity is checked, the first hypothesis of mean value theorem. Let me find the derivative of this one and see if it is if everything holds or not. So that one will be 4 over 5 x to the power of 4 over 5 minus 1. The power is decreased by 1 in derivatives. So that will be x to the power of, this one is equalizing the denominators, minus 1 over 5, 4 over 5, the negative brings it down the denominator, so x to the power of 5. Is this one differentiable on the open interval of 0 and 1? That function is only making problem at 0, and 0 is not in the interval. Why I'm not writing the closed interval? Because the hypothesis says continuous on the closed interval and differentiable on the open interval. Okay, that's why I changed the the interval into an open interval. Since it is making a problem in 0 and 0 is not in the interval, open interval, so the differentiability also holds. Okay, so both of the hypotheses hold, so we can say that that function is holding the hypothesis of mean value theorem, and we can apply the mean value theorem to that function, or we can say we can find a c that is between 0 and 1 such that f of c is equal to, f prime of c is equal to f of b minus f of a over 1 minus a. Three more examples are given. You can check the other examples yourself. You're just checking if the function is continuous on the given interval and differentiable, taking the derivative of the function if you could. Checking this once, you can see if it holds the hypothesis of mean value theorem or not. That's all about section 2 of chapter 4. I'll move to section 3 later. Hope you would understand the subject easily and well. Thank you.